All right, ladies and gentlemen, as promised, a couple more related rates examples. This one I like because it uses trig. So we have a hot air balloon rising straight up from a level field. So that gives us the right angles I'm going to need. So here's a level-ish field, hot air balloon. I'm just going to put it up there. I'm going to represent it with a dot instead of a picture of a hot air balloon. It's tracked by a rangefinder. So there's the liftoff point right there. That's straight up and down. It says tracked by a rangefinder 500 feet from the liftoff point. So somewhere over here is a rangefinder, which is like a thing that measures distance. That's 500 feet. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 3 radians per minute. Holy cow, that's a lot of stuff. So basically, there's the balloon, and it's over the liftoff point. And now the rangefinder is pointing this way. I'll call maybe this X and maybe this Y or something. That usually is smart to call vertical distance is Y and horizontal distance is X. But this time is a little different. X is not changing. Y is changing. And there's an angle here, which is going to be important, I know, because they started talking about the rangefinder's elevation angle. Maybe we call this theta. We usually use that letter, that Greek letter, to denote angles. So I've now named everything. That's 500. It says name variables and constants. It's tempted to think that this is a constant, which of course it is, but like that's at the end, after we take the derivatives, we're going to plug this in to figure out whatever we're trying to figure out. When it says at the moment, that it was like up here, it said at the moment, the base is 12 feet away from the house. Before I plug that number in, I got to get an equation. So if I plug this in first, everything's just going to turn into 0. So I don't want to do that yet. So this 500 never changes. So that's a constant, right? No matter how high the balloon goes, the distance from here to here is always 500. This is changing with respect to time. So it's not technically a constant. And so even though this is here, you don't want to plug it in until the end. What am I trying? So what am I asked? Okay, and also, yeah, this 3 radians per minute is we'll talk about that in a minute. What am I asked to find? Oh, how fast is a balloon rising? So the way I drew this picture, that would be dy dt. I'm trying to find that. I don't know what that is. Write an equation that relates to the variables. So the variables here are x, y, and theta. And in a right triangle, the way this is written, the thing that relates an angle, the opposite side to the angle, and the adjacent side to the angle is a trigonometric function called tangent, which you may remember, SOHCAHTOA and all that. So I can write the tangent of theta equals opposite, which is y, over adjacent, which is x. So that relates to 2 variables, y over x. I know that x is not changing, which tells you something about dx dt. Y is changing, so that's what I'm trying to find. And theta is changing as a balloon rises, theta gets bigger. So I would expect dy dt and d theta dt to both be positive. And dx dt is going to be 0 because this distance is always 500. So differentiate with respect to time. So the derivative, I'm going to do the derivative of both sides. This derivative of tangent of theta with respect to time is secant squared theta times d theta dt. And the d theta dt comes from the fact that if I do derivative with respect to time of this equation, this is a t, but that's not a t, that's not a t, that's not a t. So this over here is going to be, since this is a quotient of functions, y divided by x, when I take the derivative of the right side here, I'm going to have to use the quotient rule, which says the derivative of the top times the bottom. So that's dy dt times x minus the derivative of the bottom times the top, which is dx dt times y, all over the bottom squared. So that's x squared. So I've done that, and now I got to evaluate. And let's see. So the thing is pi over 4. So I'm gonna have to draw that picture again because it's not so obvious maybe what's gonna happen here. I have a triangle. I have theta, I have x, I have y. X is 500 because it always is 500. So let's see. Secant squared theta dy. So this is why dy dt. I'm looking for dx dt is 0. I'm writing down all the rates I know, and d theta dt. Remember, now that I'm evaluating, I'm going to use the numbers they gave me. So this is going to be what was it? Was it 3? Yeah, 3 radians per minute. So I was about to write a pi, and that's clearly wrong. So the d theta dt is 3. So, okay. So secant squared theta. So theta is pi over 4. The secant of pi over 4, let's see. Secant pi over 4 is 1 over cosine pi over 4. Pi over 4 is 45. Cosine of 45 is root 2 over 2. So this is 1 over root 2 over 2, which is you flip over the bottom and multiply by 1. So I get 2 over root 2, which is actually equal to the square root of 2, turns out. Secant of pi over 4 is square root of 2. You put in your calculator, you get 1.414 or something, but I don't want you to have that number. So I'm going to square this anyways because it says secant squared theta. And when I square this, I get 2. D theta dt, I was told was 3, and it's positive because the angle is getting bigger. Dy dt is what I'm looking for. So dy dt, I'm just going to leave in there, times x, which is 500, minus dx dt is 0, so I don't really care what y is. And then x squared is 2,500. 25 with 4 zeros. Yeah, that's right. So sure. Now I got to solve for dy dt. This is 500. I don't have to worry about that. Minus 0, so I can cross off that 0 and that 0 and that 0 and that 0. So I got 5 over 2,500, which is 1 over 500. So 2 over 3 equals dy dt over 500. Multiply both sides by 500. This is 6. So dy dt is 6 times 500 is 3,000. And what the hell are my units here? Minutes and feet. And since this is a rate of change of like the height, it's 3,000 feet per minute. It's actually going really fast. It's a very, very high velocity, vertical, high vertical velocity for a hot air balloon, but so be it. I think that's because 3 radians per minute is actually a pretty significant increase in angle. So that's your answer. Like I said, this one was trickier than the other one because we used trig functions. The picture is a little different. And like once you differentiate, you have a more complicated thing here, but like there's really nothing that different about this. It's just kind of getting used to what the different pictures look like. So maybe I'll do this one here and I can do the cone one in class before we start working on the classwork. This one's a little shorter. So 2 cars start moving from the same point. One goes south, one goes west. So I'll put the point here. One goes south at 60 miles per hour, and one goes west at 25 miles per hour. At what rate is the distance between the 2 cars increasing 2 hours later? So it's tempting to write 60 here and 25 here and like be like, all right, what's this number? But that's not how this works. Because this 25 is not how far the car has traveled. This 25 is like how fast this is changing, right? This is calculus, so we deal with rates of change a lot. So really, if this is x And I should have erased this too. And this is y. Then the 25, it travels west of 25, is dx dt. And this is the 60 is dy dt. And I'm trying to find this distance. I don't know what it is. I'm just going to call it z or something. But I'm not actually trying to find z. I'm trying to find dz dt. It doesn't say what is z 2 hours later. It says at what rate is the distance between the two cars increasing. That's what this dotted line represents. And I'm going to call that z. So I'm trying to find dz dt. So I've done this, and now I want to set up an equation that relates x, y, and z. These are all three of these are changing. And I know since this is a right triangle, since south and west are 90 degrees apart from each other on the compass, that x squared plus y squared equals z squared relates all of those. And I have this 2 hours later, which I'm going to deal with in a minute. But like, I don't want to plug any numbers in for x, y, and z yet, because if I do, then I'm going to get a lot of zeros, and that's not very helpful. So I'm going to differentiate with respect to time, this whole equation. So derivative of x squared with respect to t is 2x dx dt. Remember, implicit differentiation. Derivative of this thing with respect to time is 2y dy dt. The derivative of z squared is 2z dz dt. These are all the same derivative. And I know I can cross off all the 2's because there's 1 in everything. That makes this a little easier. And I know a lot of these things. I know dx dt is 25. I know dy dt is 60. I know I'm trying to find dz dt, so I don't need to know that yet. But the other things that appear in this little equation are x, y, and z. And this is where the 2 hours later comes into play. Like it's not that x is 25. It's that after 2 hours, if a car is moving 25 miles per hour, that car has moved 50 miles. That's kind of the thing you're supposed to see here. Which makes sense. 25 miles per hour for 2 hours is 50 miles. 25 miles each hour, 2 hours, 50 miles. So at the point exactly 2 hours after these cars leave, x is 50. By the very same logic, since it's going, the other car is going south at 60 miles an hour, its distance is 120, y is 120, and I can find z by using Pythagorean theorem, and I'm pretty sure it's 130. This is a 5, 12, 13 right triangle. 2 hours later implies these three numbers. Now I just plug all those in. X is 50, dx dt is 25, y is 120, dy dt is 60, z is 130, and then dz dt I'm trying to find. So I would get out my trusty calculator and I would do 50 times 25 plus 120 times 60. And I get this big number, 8,450. And that's equal to 130 dz dt. Divide both sides by 130. And I conveniently get that dz dt is 65 miles per hour. I know it's miles per hour because that's what all the rates are measured in. Everything was in miles and hours here. So that's a Pythagorean theorem kind of question. Another one. Remember, the ladder problem was a Pythagorean theorem question. This one looked like a Pythagorean theorem question at first because there's a right triangle, but because they give me this angle situation and the d theta dt, I don't really have enough information to calculate this thing. Theta has to be in my equation because that's one of the rates I was given. So I had to use trigonometry here. Here, since all the rates I'm given are x's and y rates, I don't have to worry about the angle in between them. So like I said, I'll talk about this cone one in class. Cohen's are a little tricky. Also because this is just 100% not the right equation for the volume of a cone. So please ignore that. That should say 1/3 pi r squared h. That's yikes. That's terrifying. All right, so ignore this. This is the right formula, but we'll talk about that in class anyways. I'll see you guys then.